several hours testing this afternoon. And there we go. Now there should be sound on the stream. Ah, see? Now there's sound. That means the recording won't have sound either. That's okay. I haven't said anything important at this stage anyhow. It's just logistics crap. I strongly encourage you to collaborate with others. If you want to put 154 people all in the same room and all talk about this stuff at the same time while you do shots or something, I'm fine with it. Don't care. If that works for you, do it. If you're the lone wolf type, you can make that group 153 people and you can stay in your abode and do whatever it is you like to do when you're studying. That's cool too. Whatever works for you. You should use the tools that are available at your disposal to answer these questions. You know what? You can take that book, you can feed it into ChatGPT, and you say, yo, chat, would you please summarize chapter 5 for me? And you know what? Chat will do it. I don't know, have any of you started using chat to do that? Literally take books and summarize them for you? Don't trust it. I had to generate some questions for the class, and they were wrong. And then I said, okay, well, explain to me how you got to that answer. And it changed its answers while it was explaining them to me. And I called it on it, and it was like, oh, yeah, sorry, I made a mistake. It hallucinates. It's very interesting. If you prefer, you can just talk to your hamster. One of the best design colleagues I ever had was my dog. He would listen to me, unlike you. He would listen to me. And he would just give me that sweet look of understanding. Well, that and, food. Don't forget to submit it. If you didn't submit the last one, then please don't miss any more, because you've now chipped away a small percentage of your safety net, as it were. Is there anybody in here who submitted it? Nobody submitted. Oh, one person submitted it. 3 people submitted it. I know you're lying because I saw the numbers yesterday and it was like 54. So, but you'll notice I also asked the question so you didn't have to admit you didn't do something. I've learned over years of teaching that you don't ask questions to require people to admit they don't know something. You only ask them to admit they do know something. People think that not raising their hand is not a lie of omission. You can ignore those. But they won't raise their hand and say, oh, I know about that, when they don't. Very interesting human psychology. And, I moved the mouse. So, of course, I have to come back and move the mouse back onto the window. And now it will click again. Right, so today's failure, keep it short and sweet. This is one that came across my feed just a couple of days ago. Microsoft had 3 staff at an Australian data center campus when Azure went out. The best part was apparently it required at least 5 people in order to restart the chiller, which had failed. And I love the description because it talks about how, well, things got a little toasty. And some of the hardware baked. It's like you probably have friends who get baked too. Fine. It's not the most effective thing to do with your data center, just like your friends don't do their most effective studying. Well, then again, I have friends who program, and there's this whole thing called wake and bake. It's real. They don't do a lot of military government kinds of contracts, but they still say fully employed. And the descriptions are very milquetoast. This created issues affecting access to Azure, Microsoft 365, and Power Platform, i.e. all of the critical Microsoft services that Microsoft provides to businesses who pay them real money. They didn't provide any financial analysis here, but I'm willing to bet you that the cost of this was measured in the millions, if not tens of millions of dollars. This is what happens in these distributed systems. I'm not going to go into great detail. There was a power sag, it killed the chillers couldn't restart, the hardware got hot, and then a bunch of things that were supposed to recover automatically didn't quite work right. This is why distributed systems are hard. The cases we care about are when things go bad. Our testing focuses on when things work right. How do you test when things don't work right? How do you simulate a power failure? How do you simulate a disk drive melting down? How do you simulate a cyclone blowing through and destroying a data center? The reality is the problems at this scale are so large, the only place you actually get to test and deploy is in production. And if that doesn't scare you, you must really like horror movies. But that's the reality. Cascading failures are very common. This was a nice example of cascading failure situations where we have all these layers of backup of things that are supposed to back us up when something else goes wrong. And, well, you know, this fell off and that thing didn't work and this fire retardant didn't go off and then we didn't even have enough people to restart the chillers. Staffing issues. How many months could they get away with having inadequate staff? Probably for a year, and nobody would notice. And when did they notice? When they needed that staff there. Murphy was an optimist. Anything that can go wrong will go wrong. Anything you think of that can go wrong will happen. Things that you've never even imagined going wrong will go wrong. How do you test those? I'm going to give you the DS Labs, and I'm going to point out to you that it's a tool. Is there anyone in here who knows what a discrete event simulator is? One person. Maybe that's the person who asked me about DS Labs on Discord, because I was explaining what a discrete event simulator is. So a discrete event simulator is a single-threaded program that has a time-ordered queue of events. The single-threadedness means we don't have to worry about things like preemption. When the loop that processes the event says, I need something to do, it takes the next event on the queue regardless of what the time is. So what happens is, when we start the simulation, we put an event somewhere further in time. Let's pick an arbitrary number. Let's say 36 million years. So 36 million years from now, our simulation is going to stop running. Okay. Now, if you don't put anything else in the queue, we start at time 0. Next time is 36 million years. Wow, we just simulated 36 million years in a few nanoseconds. This is one of the benefits of having a discrete event simulator. We don't actually have to wait for the clock to run down. Why is that a useful tool? We're going to be talking about networks. 99% of the time, networks deliver packets in the order in which they were sent. 1% of the time, networks don't deliver packets in the order in which they were sent. How do you simulate that 1%? Because that's the failure case. That's the case we're interested in. How do you simulate that? Well, in fact, in the DS Labs, what happens is when you send a message, it pulls out its magic pseudo-random number generator dice and throws them and says, this is the time that message is going to get delivered. And it has a separate mode that says, this is the probability we're going to deliver it at all. So we can have a loss rate, and we can have an arbitrary delay in the network. But this isn't deterministic. Well, it's pseudo-random, so of course it's deterministic in that if you start with the same seed, you're going to get exactly the same outcome. So that is one benefit of this kind of simulation. But it's going to drive you crazy, because all of a sudden, all of that mind-bending, twisting asynchrony logic that maybe you remember from 313 is going to slap you square in the face and go, ha ha ha, it's real. It could really happen. It is very hard to think about events that happen in arbitrary order. This is a tool that actually causes it to happen at a higher frequency than it will necessarily happen in reality. Furthermore, the tool does that by varying parameters to search through the space of possible orderings of these messages. So it can be not just pseudo-random, but it actually can be deliberate in choosing to deliver those messages in specific out-of-order sequences that are interesting. Next week, I think it's next week, we're going to have a guest lecture by a grad student here who does work in formal verification and modeling. And so I've asked him to step in and give a talk because he's going to do a better job of explaining it. The idea with formal verification is, imagine that you could formally describe your system and run it through a solver that proves that certain conditions are never violated. They're what we call invariants. The purpose of the invariants are to say, here are things I know will always be true. For my system to be working correctly, this must be true. And I'm being vague deliberately here because what must be true is part of what you have to define. So if you give it the wrong set of invariants, you're going to get potentially bogus results. The biggest problem with this kind of formal verification is that in order to verify the invariants, you have to do an exhaustive search of all of the possible ordering of events that can happen in the system. The problem with this is that becomes explosively large. It blows up. So instead what we do is we use a simulation of that. So we do modeling. We create our model, we have our invariants, and then we sample and try to find cases that violate our invariants. When they violate an invariant, the program stops. That's what DS Labs is. It is a tool that establishes a set of invariants. Those are the test cases. It has a set of invariants, and it runs them in a discrete event simulator, a single thread with a big time-ordered queue. Every time a handler gets called, it can put something in that queue. Yesterday, I was answering a question about this for the Georgia Tech class, and somebody was explaining to me that they didn't understand what they should do when they were implementing at most once semantics. So the idea with at most once is you have a client who has the at least once semantic. And we have a server that implements at most once semantic. And between the two of them, it means we have exactly once semantic. Because when we put those two things together, the intersection is it only happens one time. So the idea is that a client sends a request. If it doesn't hear an answer back within some finite bounded time, which the client gets to choose, it sends the request again. It doesn't ever progress to another request as long as the current one hasn't been answered. That's the at least once semantic. At least once you are going to answer me. At least once you're going to answer me. At least once you're going to answer me. And eventually you answer me. Or I just keep sending messages and nothing ever happens. The server receives that request and says, the last request I received from this client was this number. There's a sequence number. It's a Lamport clock, a monotonically increasing number. So it always goes up. So I look. There's only really two possibilities there. One, the number that I receive is greater than the last number I saw from this client. And if that's the case, then this is a new request, and I'm going to execute it. The other option is this number is equal to or less than the last request that I processed for this client, this specific client. We don't have a global clock, we have a local clock, just the client's clock. And if it's less than or equal to, if it's less than, the answer is, the way you handle it is you just drop it. You just go, this is like yesterday's news. I'm not doing this. I've not only answered you, but you've sent me another request, which tells me that you received my response. So I don't need to do anything at all. This is just some packet that the network held on to for a couple of months and then say, hey, look, here's this like 2-month-old packet. I'm sure you still want. No, not really. It's like a 2-month-old Timmy's donut. No, the only thing I want to do with that is throw it in the trash. And if it's equal, you send back the response you sent last time because maybe the response didn't get delivered. And this is just networking at its finest. But this is one of the very simple paradigms that we use in the DS Labs in order to implement that functionality exactly once. And that's going to be really important because we're going to use that mechanism for creating robust consensus protocols. So what were the goals? Why do I have you reading this stuff about B trees and file formats and whatnot? And the reason is that last term I learned that people don't know anything about how databases and file systems actually work at all. Not a bit. And it's kind of hard to be sitting here reasoning about building these distributed consensus protocols that are ostensibly replicating these things when you don't know what these things do or how they do it. At every level, we have to think about, how am I going to recover from a failure? What kinds of failures can you get with an SSD? That's not rhetorical. That's actually a question for the class here, seeing if anybody's awake. I mean, it is actually after 5, so it's probably time to take your nap before you go out and party at 10, right? It's Vancouver. Everything shuts down early. It's not as bad as MIT. MIT, everything shuts down at 1 p.m. All the bars are closed. Not that people at MIT go out drinking. What could go wrong with an SSD? There's a hand in the back. You were saved. I was looking at you. I was going to pick on you. There's a hand in the back. Yes, sir. After a while, you can't write onto it because SSDs have a write lifetime. They suffer from what's called write wearing. Okay, that's a pretty exotic failure, and it usually happens long time, but yeah, yes, absolutely. You're not even thinking of very simple things like, gee, I kicked my power cord out. Have you ever accidentally unplugged your computer? Or, let's see, maybe your laptop battery ran out? Yeah. Well, what happens to all the data on your SSD? It doesn't disappear. But what about the data that was in memory that hadn't been written to the SSD yet? It's gone. It's gone. So that's a pretty common failure. Power failure is an example of that kind of failure. Probably the most common. You get pretty much the same result if the operating system crashes and reboots. And operating systems do crash occasionally, and they do reboot. And then there's some application programmer that dances for joy, because the goal of every applications programmer, certainly from the perspective of any systems developer, is to crash the OS. It's a goal. You achieve it, you dance a jig, and then you go on with your life. And the systems people have to try and prevent this from happening. It's an adversarial relationship. It always has been. It always will be. Okay, so here we are. We're talking about the data structures that we're actually storing on these devices, because if I want to maintain consistency of these data structures, I have to be able to reason about what am I going to do when things fail. So maybe I should know what they do when they work. It's kind of like, studying medicine, because we're in a medical building anyway, and you go to the pathology lab and all you do is look at dead people. Well, how do you know what kills something if you don't know what it's supposed to look like when it's alive? I spent like 20 years teaching post-mortem debugging on Windows, believe it or not. And I always would try to show people what live systems looked like and then compared it to dead systems, because you can't really figure out what killed it if you don't know what it's supposed to look like when it's alive. And so this is what we're doing. We're going through this exercise because I want you to have a better understanding of the way that these critical data structures actually function. And the reason that this becomes important is because when something goes wrong, we need to be able to get it from, sorry, this is screwed up, to, oh, everything is hunky-dory and wonderful and life is good. That's recovery in a nutshell. So chapter 3 is talking about file format. How do you organize data? We do it for performance reasons. We do it because it allows us to recover things more easily. Because laptops die, power goes out, power sags in Australia happen. It's not like I'm just making this stuff up. These really happen in the real world. It took Microsoft 2 days to recover from that failure. 2 days. That's why I said I'm sure the number was probably in the tens of millions of dollars. Australian, which is probably about tens of millions of dollars Canadian. I don't know, anybody know what the Australian dollar to Canadian dollar ratio is right now? No Australians here. Huh. How disappointing. B trees. Well, when you think B tree initially, maybe you thought binary tree. Well, these aren't quite like binary trees, but they're multi-array trees. So instead of having a left node and a right node, we have an array of left nodes and an array of right nodes. But it's the same basic idea. The reason that, of course, we have more than one is that storing a few values in 4K of storage space probably isn't the most efficient way of actually storing data. So we have this block structure, and that block structure of the underlying device does profoundly affect the way we organize our data structures. This is really what happens in systems. We end up building solutions specific to the technologies that we are given to use to implement our product. If you were doing this all in memory, you wouldn't be doing it this way. This is kind of dumb. And there's actually a whole conversation about that, about what the differences are between, some of these aren't really big problems in memory, but they're more interesting problems on disk. Are you familiar with the concept of garbage collection? I'm sure you've used Java, right? Which is a great language for just like randomly stopping the universe while it goes and cleans up. Garbage collected languages are not good for real-time systems because garbage collection languages have exactly this interesting behavior, which is they stop and they garbage collect, which means they compact the space they're using, they free up the space they're not using, and then they let everything resume. And that's really bad if you were running a, like a, I don't know, a cardiac pacemaker. Don't worry, 5 minutes without your pacemaker, you'll be fine. There's so many good medical analogies since we're in a medical building. It's great. I like that. In chapter 4, I thought there was some interesting things there. It's like, how do we handle mutability? Do any of you know the basics of computer processor architecture? Must have had some sort of hand-wavy thing there, right? Well, I can tell you that all of the current processors only allow mutability in the level 1 cache. Maybe that will surprise you a little bit. The reason for that is mutability makes the world much more complicated to reason about. So when we have a multi-level cached processor, we only cache things in one level of the cache, and the only place we mutate them are in the level 1 cache. It's the fastest, most expensive memory, and it is, because it's the fastest and most expensive, and it's the only place it's mutable, the larger areas are much simpler. Mutability makes the world much more complex than immutability. If you can make things immutable, the world is way simpler. Have any of you heard of this thing called Facebook? It turns out that people share lots and lots of personal information on this service, including slightly embarrassing pictures that they share with their friends. And then they realize the next day, after a night of that casual drinking, talking about 416, you wake up and you go, I really shouldn't have posted that picture. So you go to Facebook and you delete that picture. Do you know what Facebook actually does? They don't delete it. No, they have a blacklist on the front end. They have a list of, here are all of our deleted pictures. So the first thing that happens is somebody tries to click on that deleted picture, and it goes to Facebook, and Facebook looks up in a list, some sort of binary tree actually, and it says, hey, is this picture on the blacklist? And if it is, I'll just send you back, sorry, couldn't find it. But you don't actually delete it from the storage. It's actually still there. I mean, in theory, you can go back and delete them, but it turns out that that kind of space reclamation is extraordinarily expensive. I convinced somebody else who does work in host-managed shingled magnetic recording drives, and she does garbage collection on disks. because they're log structured. They're all log structured, and so you have to reclaim space on them. And they're zoned, so you're reclaiming space in large chunks, like 256 megabytes kind of thing. And it's very interesting when you actually talk about how do you do this kind of garbage collection extremely efficiently in a way that doesn't impact performance. Because just like the Java virtual machine can sit there and just freeze everything, if you're not careful, your disk drive's garbage collection unit can sit there and freeze everything, except the times are now really measured in milliseconds per operation. So you don't really, you didn't really need to use this thing for the next 5 minutes, did you? I mean, this is only a real-time database that we're actually using to run Amazon. You can't do that. You have to be very careful about how you do that work. So these aren't just make-believe. One of the reasons I like Petrov is because Petrov is writing this from the perspective of somebody who's working in this field and really implementing these systems. This complexity is not arbitrary. It's not made up. It's actually what we do. How many of you are going to work for, I don't know, Amazon, Microsoft, Google, IBM, Oracle has a group here that does work in this space. How many of you are going to get a job? Or are you just going to go back home to mom and dad and hang out in the basement and play video games? Yeah! Drink bubble tea. Too much sugar. Might as well eat donuts. You get the fat that you need too. So let's talk about this. I've rambled a little bit. You've now read this stuff, right? How many people actually read chapters 3 and 4? There's more hands that just went up than people who admitted they did the self-assessment. Very interesting. Why would you do the work and not do the assessment that gives you credit for the work? Did you find it confusing? A lot of detail there, isn't there? Okay, fair enough. What did you find confusing?
The concept of overflow. A variable size values.
It's like stretch pants, right? Overflow pages, yeah.
Yeah, it one out of space. These are extra pages. How do you perform binary over such a thing? Have your data.
You need an indirection, right? So you don't sort the data in its physical location, you sort the data in its logical location. Well, that would be one possible solution. Can you imagine any other potential solutions besides paging in your entire linked list before you process over it? Think page tables. Right? Page tables are collections of physical pages that are in different locations but are virtually contiguous. You don't have to bring the whole page table in order to find things that are virtually contiguous. So that's one potential data structure. It's not the only data structure, but it is one potential data structure. This is a really important question because when I reach into my bag of tricks as a systems programmer, I have basically like 3 tools to pull out. And one of them, and it's my favorite tool, is the extra level of indirection. Why do anything directly when you can do it through a table lookup? That's what virtual memory is. That's all it is. You know, they spend a lot of time making it sound really grandiose, and then you realize it's just a table lookup. You take a logical address, you turn it into a physical address. That's it. You had a question. No. Did we had a, oh.
No.
Sorry? Oh, okay. Well, you can ask again, and then everybody else can benefit from it. Oh, okay. Cool. The breadcrumbs? That was earlier. Oh, okay. Everything else is perfectly clear. Nobody else had any other questions? This is going to be a really short session. This is awesome. He has friends. I don't. I'm jealous now.
Now you have a
all the how do we go from the on the graph there actual how do you go up level?
How do you go from the upper level of a tree to the lower level of a tree? One node,
Yeah.
right. How do you go from the upper level of the tree to the lower level of the tree? What's in that node? So this is a pointer, right? Okay, so what does that pointer represent in this instance? This is a disk drive, or something pretending to be a disk drive, because SSDs pretend to be disk drives. Hi, I'm a disk drive. I don't have anything that rotates. I don't have any heads that move over magnetic media, but I'm going to act just like a disk drive. So how do you address things on a disk drive or on an SSD? Right. What is the address? Oh, we're getting circular here now. It's a disk pointer, yes. All right, so we've got these sticky note things over here. All right, so in an actual rotating drive, the way that we reference things is by providing a cylinder number, a platter number, and then an offset number, a sector number. So it's 3 dimensions, and we specify those 3 dimensions. That becomes the address. Well, it turns out that through this amazing thing called math, we can actually map that 3-dimensional thing onto a 1-dimensional thing. So we can just linearly number these things. And that's what we do. So the simplest way to think of it is we just give every block on the disk a unique number. And because we're lazy, we just make them, increasing unique numbers. So 0, 1, 2, 3, 4, 5. We could keep going on this. But does that make sense? So the way that you know where to go next is because when you created that node and you added the next node down, you kept the address of where you stored the next node down. But of course, there's nothing that prevents us from pulling out my favorite tool, the extra level of indirection that says that address is actually a lookup in a different table, which then points to that location. And the reason I would do that is because maybe I want to move where the data is physically located to another spot. That's the way SSDs actually work. I was talking about log structuring. In an SSD, when you write to the SSD, it actually writes the data to a new block. Even if you're overwriting an old block, it writes the data to a new location on the SSD, and then it updates a table that says, oh, that block is now here. It literally just adds 1 level of indirection. So we've got this whole little 3-card Monty thing, where there's a P under the shells and you move it around, and right, you got to figure out which one it is. And I get to just simply redefine how things work under the covers. And you pointed that, and there's a P there. Okay, great. Well, but that's not the same P it was before because I replaced it. And the reason that works is because as long as it has the right data in it, nobody's going to notice. It's a great trick. It's the same trick we played with virtual memory. Right? Why did we do virtual memory in the first place? Well, because we know that disk drives are almost as fast as memory. Right? Yeah. Virtual memory allowed us to create large address spaces when we really only have a small amount of memory. We can overcommit, kind of like, going to UBC as an undergrad, right? Perpetually overcommitted. And then you thrash. Constantly trying to swap context in and out. Great question, though. Really good. Does anybody else have another question? He's already asked one. Ah, there we go. And you'll get a chance again, but I'm designing a storage into, you know what? I have this amazing technology so that people could actually hear on the recording, and I don't have to remember. So you can talk, and they will be able to hear you. So cool. You just hold it.
So if you're designing a storage engine for a database, would you always keep the beep tree index in the main memory?
If I was designing a storage engine for a database, would I always keep the main index in memory? That's a really good question. It deserves an equally good answer. Next question. I want to get 2 volunteers on this. I want one person to volunteer to argue yes and the other one to argue no. Come on, step up to the plate. Well, could you repeat the question? So, if I was designing a storage system for a database, would I keep the index in memory? And now you get to take. Which advocate are you going to advocate for or against?
Only in memory, or is
You're the advocate now. You get to pick.
no? But did he say it?
He didn't say either one. He just said in memory.
Oh, I would say in like persistent storage as well.
Okay, so your answer is both in memory and on disk.
Okay, I mean, if you're using it actively in memory, but if it's switched off, you need a persistent storage.
Is that true? And now everybody freezes and goes, oh my gosh. Now, the best part about this is there's no wrong answer here. So you have the chance of saying something and it being the right answer, because either yes or no is the right answer here. There are systems that do both of these.
Can we have more than one of the memory?
Can you have more than one memory?
Yeah.
What does that mean?
Yep. Many systems.
I have many systems, so I could have, okay. So I think maybe what you're saying is, could I have different computers that have different information in their memories?
Yeah.
Yes, that's called sharding. That's Project 5 in the DS Labs.
Oh.
And that's the one that usually really totally screws with people's heads. I had a single student last term who got 100% on that. Most people got about 60. Aren't you glad that you're not going to be graded on that at all? And it is a brutally difficult problem to solve in the DS Labs, and yet it's like a trivial example of what you really do in the real world. So he said, no, you need to store it both in memory and on disk. I now need somebody who's willing to take the opposite perspective. And now, given the way he answered it, the opposite perspective could be, no, you only keep it on disk, or no, you only keep it in memory. Everybody's looking down going, oh, please don't call on me. Please don't call on me. Please don't call on me. Okay, fine. This will be a really good question for the final. Thank you very much. Did you want to take a stab at it? All right, you volunteered.
All right. So I would like a clarification. What do you mean by keep in? Because to operate on the memory at all, you need to page it into main memory.
I don't know. I didn't ask the question. He asked the question. He made up the answer to one of them, so you ask them. Or better yet, since they left it ambiguous, you can choose either one and give your answer.
I would say that for a database to remain persistent, you would want to store the index in disk, and as needed, page it in. If you need to access that index, and go find your value for your key, so that if your computer does shut down, your main memory index isn't gone forever. That's my argument.
Thank you. I mean, actually, that was really useful. I enjoyed that conversation. Have you ever heard of memcached? Memcached. Do you know what memcached is? I've heard of it, but I don't know what it is. It happens to be a key value store that lives entirely in memory, hence the name memcached. Why is that a useful example? Because that's a case where everything is in main memory, nothing is persistent. Whoa! What do you do with that? All right, well, here's a question for you. Have any of you guys ever used this thing called the internet? Have you ever used a web browser? Have you ever looked at what a web browser actually does? These are kind of rhetorical questions. I'm assuming, of course, you've all probably looked at a web browser, and you probably all know that you can actually pull up the developer's console in a browser and look at it. Web pages are made up of a large collection of what are called assets, objects. There can be hundreds of them for a single page. Hundreds. It can take time to assemble all of those objects so they can render. I mean, I have websites I read where the thing never stops flickering because it's constantly loading more objects into the page, and they didn't have the right size, so they didn't draw it correctly, so they keep redrawing the darn thing, and it's annoying, and eventually I just give up on those websites. Okay. How do I speed up the acquisition of those objects? I cache them. Great. How do I know how to find something in the cache? I take its URL, I hash that URL, and that then gives me a key. Wow, this is almost like topical, isn't it? It's so cool. And the value of that key happens to be the object. And the nice thing about this is I'm a cache. I'm not really a kind of classical database where people are updating it. I am a performance optimization. And so I can keep everything in memory in that case. Now, literally, people build these Memcached servers with terabytes of RAM. Do you know how long it takes to load a terabyte? A terabyte of data off a disk drive, off of an SSD. It's measured in tens of seconds. Actually, I think 1 terabyte takes about 6 minutes, if I remember right. That's the last time I did that computation. And I did that because I was working with non-volatile memories. Intel had this product called Optane, which was available as a DRAM replacement. And the primary benefit of it was that it was very high density. You literally could have, in the space of 64K of DRAM, you get a 64 meg of DRAM, you get 512 meg of non-volatile memory. So I was working on machines with 6 terabytes of non-volatile memory. And I had to do the computation because it was like I actually published a whole paper about this weird behavior that I saw because of the cost of paging. And paging is completely unrealistic in this scenario because no one is ever going to page something that is so large that it requires 6 terabytes of memory to put it in the memory. It just takes too long to get it off of storage, even if you use SSDs. And 6 terabytes of SSD, I mean, that's several of them put together, not just one. That's not true. You can buy 6 terabyte SSDs. They're just really expensive, like $50,000 kind of expensive. Okay. And it's going to take you like 6 minutes to load it. So nobody actually loads that instead. It's a cache. The system still works if the cache gets flushed. So one of the interesting things to realize here is that it depends on what the use of the database is, whether or not I'm going to keep the index in memory, on disk, or some hybrid version of that. Real databases, the kind that you're thinking about when you were probably asking the question, the real databases, like, I don't know, Oracle, SQL Server, MySQL, those kinds of databases are going to end up with a hybrid model where they keep frequently used information, parts of the index, in DRAM, and they're going to keep other parts of it in persistent storage. And the interesting thing there is going to be, how do you organize this? And this is not like a quiet, quiescent sort of field. There are a steady supply of academic papers and industry papers about different ways of approaching this problem and making it run fast and recoverable, because this class is about failure and how to deal with it, and nothing pisses people off more than telling them, I'm sorry, your database is toast and you get to go find your backups of it and restore it, because that's going to take you days. Amazon had a project called Snowball. Big company. A big company would come to you and they would say, we want to move our data into the cloud. We have like 65 petabytes of data. Go do the computation. How long did it take you to send 65 petabytes of data to Amazon over the internet? And this is a very interesting piece of analysis. You may have even heard it because it's very common. It turns out that the bandwidth of the internet and the bandwidth of a van full of storage devices have been pretty close in terms of their bandwidth capacity multiplier, when you do the ratio of them. In other words, if I take a van and I load it full of SSDs filled with data and I drive it to the other side of the country, it still has more bandwidth than the entire internet. The latency sucks. You don't want to game over that particular network, but the latency didn't matter in that case. So Amazon actually built this project called Snowball, where they brought in a truck. Like, they've custom built these 18-wheel truck trailers, and they would bring it in, they'd back it up to somebody's data center, they'd siphon all the data off, and then they would drive it to Amazon and offload it there. I kid you not. That time is measured in weeks. You can't do that for backups. You can't require somebody spend 6 weeks out of business while they get their database back up. It doesn't work. There's a question back here. He's been very patient, so now he gets to be on the spot.
Oh, so I was asking, like, in the hybrid model, right? So would the frequently accessed stuff still be also stored inside the persistent storage, or would it be only on the memory? Like, what if there's a power outage?
That's a great question. So his question was, okay, so yo, fat dude, you've given me this you've given me this hybrid model. What do I do about that data that's in memory? How am I going to make sure that's safe? And that is a really good question, because this is kind of the whole point. Why am I forcing you to read all this stuff? Because every bit of this is about optimization. And one of the optimizations is trying to find a balance between how much I put in persistent memory and how much I keep in transient memory, ephemeral memory. Real storage systems, real databases with real storage systems actually have learned that almost all of the data in the database is dead. They call it cold. I mean, it's isn't cold, like it should be in the cadaver lab because nobody's accessing it. Does anybody know what a zettabyte is? It's 1,024 exabytes. We generate about 5 zettabytes of data a year right now. And that number is roughly doubling like every 2 years. So it's probably up to about 10. So it goes tera, peta, exa, zetta, yada. We already have people who are talking about yottabytes. We will hit a yottabyte of data within the next 10 years. There's a lot of this data. Almost none of it is actually used. Just like the pictures that you take with your camera phone. How many times you go back and never look at them again? No. You just scroll through them infinitely. Whatever. And then you'll meet occasionally. You will actually find people who are really good at curating their pictures. They will go through and go, I don't want that one. I don't want that one. I don't want that one. The rest of us are sitting there going, it takes too much time. It doesn't cost me anything to keep those. The only time you go and clean them up is when you run out of space. And then you just go buy a new phone, right? Speaking of which, how many people are going to order a new iPhone? I got more hands than people who said they read the damn chapters. Wow. Can't afford to read the chapters, but I can get a new iPhone with more memory on it, right? More storage. Cool. So that's a really good question. And the answer really depends upon exactly what your reliability requirements are. So, for instance, you might keep transient information in DRAM because you're putting it together, you're bundling it up, and then you send it out. When I was, God, that was a long time ago. When I was 26 years old, I was designing this whole transactional recovery system for a file system, and that was part of what we did, is that we had to keep track of what was in memory and what was on disk, and make sure that we could always get back to a consistent state of the file system. Now, this is not, nobody thinks about this anymore, but in 1990, when I was doing this work, when your system crashed and rebooted, it ran FSCK. These were Unix systems. It ran FSCK. And the amount of time it took for FSCK to run was proportional to the size of the storage. And a big disk drive, a really big disk drive, was 1 gigabyte. And it could take 12 hours to restore the consistency. What we were able to do was we were able to build a system that used journaling techniques, database-style journaling techniques, of keeping track of what activity was going on, and if the system crashed, we had enough state that we could get back to a consistent point in time, usually within a few seconds of the crash. And that was good enough. These were workstations, right? That was good enough. And we could do it in under 3 seconds. People would ask, well, how long does it take to run, to check your file system? I'm like, I don't know, we don't do that. Normally, we just simply restore the consistency of the drive in the mount operation, and you don't even notice it. I would notice it because I was looking for it, but nobody would notice a few seconds of extra time booting up. So it was a huge win. And that was a careful balance between what's in memory and what's on persistent storage, and knowing how to reason about that and saying, how do I restore the disk, which is not in a consistent state at the time of the crash? How do I restore it to a consistent state? And how do I make sure I did it right? These are great, really good conversations, really good questions. I'm really appreciating this. Anybody have any other questions? What do you think of the Petrov book? You can say it's a piece of shit. I don't care. It's okay. I actually liked the book. Thought it was really good. There's a lot of detail in there that my eyes glazed over and I went, I don't care, because it's not really important. But the concepts that Petrov teaches, the idea is that we end up picking these specific optimizations to fit the particular hardware that we're using for our persistent storage. That's really the important takeaway here. The idea that you need to understand what the formats are, because you're not going to be able to restore consistency to these databases when you're building them if you don't know what those formats are, if you don't know what it means to be a consistent database. We replicate databases for a reason. We are going to also look at how we make sure that databases that are keeping disparate data can be maintained in sync. It's kind of dumb. Does anybody know what a transaction is? Because that's coming up in the readings next. Sort of. You go to the bank machine and you put your card in and you punch your PIN in and it laughs at you. You put your card in and hopefully it spits out money. That actually is the classic example of a transaction. It means you put your card in, you put the correct PIN in, you have the money in your account, the money in your account gets transferred to the bank's account, and the bank then transfers cash into your pocket. And if any of those steps along the way, and these are clearly separate databases, the cash in the machine is a separate database from the numbers in a ledger in some bank database, because this machine may belong to a different bank even. How do we make sure that this is all or nothing? Because you're going to be pissed if they take the money out of your account and don't give you that cash. Anybody ever had that happen to them? It does happen. It's quite amazing how low the error rate is in bank machines. But that's because people get pissed when they don't get their money. I don't know, maybe you've never beaten a bank machine before. They like it. Not really. That's when they call the police and you get arrested for beating up the bank machine. That's a transaction. We're coordinating a set of changes across multiple databases. That's a hard problem. That's a different problem than replicating the database. We're going to work on that problem too. It's a hard problem too. And they're hard in different ways. So it's useful to understand what databases do and how they're organized, because now it begins to, hopefully, it makes it easier for you to conceptualize the complexity of maintaining consistency here. And the same techniques that we use for restoring consistency here, we're going to use for implementing transactions. And the same techniques we are going to use for recovering from power failures. And the same way that we are going to maintain multiple copies of the same database, so it's the same. Maybe, and then we're going to optimize that, because of course the simple way of doing this is just simply say, and this is DS Labs Project 3, which is the first design project, which is you got a primary, you got a backup. The primary is the main owner of the database. The backup is there in case the primary keels over dead. If the primary, the cleaning lady needs to plug her vacuum in, and so she unplugs the power cord for the primary server, the backup will step in and say, I can handle this now. And we promote the backup to become the primary. Simple idea. Okay, that's great. And then it turns out there's this like whole chorus of other servers that step up and go, I could be backup. Hi, I'm ready. Okay, so now somebody else comes in and says, I'm now the backup. How do you prevent them from taking over before they have a correct copy of the database? How big is this database? If this database is 2 terabytes, it's probably going to take a little bit of time. So one option is to just simply say, hey, the new primary failed too because the cleaning lady moved down the hall and unplugged a different server. Well, just promote that backup that doesn't have the whole database to primary. What is the problem with this? Well, remember, this backup started as an empty server and we're moving data over to it for the first time, right? So it doesn't matter. What it means is that we have now violated our agreement with our clients, because our clients are the applications that are using our database. And we said, we're not going to roll backwards and just throw away all of your work. And you're working for, I don't know, pick the evil company that you want to choose for your future job. Evil Corp. From Mr. Robot, right? Evil Corp. Great, okay. It's not that old. You should have seen Mr. Robot, right? Okay, fine. Evil Corp guarantees to their customers that when you use their database, they give them 99.999% uptime, and they guarantee that once they've acknowledged a transaction, an operation, a request, a command, an API call, all the same thing, different names, they guarantee that that is not going to disappear. That is what's called durability. The operation is durable. So you work for Evil Corp. You are now responsible for their primary backup system for their database. Do you ever want some half-restored backup wannabe into a position of power? No! It's not going to have all the records in it. You've violated your agreement with your clients. In fact, that's a case where the best thing to do is if you've got a half-assed initialized backup and the primary falls over, you know what you do? You stop providing any service to your clients and you raise an alarm. And then because you work for Evil Corp, you get a pager. Yeah, they give you that old-fashioned doctor kind of BS. They actually do that still. They have pager apps for your phone now. It's the same thing. And it wakes you up at 3 in the morning because you now have to go fix it manually. So this is the other interesting thing about distributed systems and failure. You can't protect against all possible failures. Last term, I actually used this like older than I am clip from Warner Brothers cartoons, where Marvin the Martian blows up the Earth because it occludes his view of Venus. You can't protect against Marvin the Martian. You don't have to. You're allowed to say, these are the failures I will handle, and no more. And usually what happens is you start off with the easy failures, like, oh, gee, the cleaning lady unplugged the server. How am I going to work around that one? And then you move to more complicated ones where you say, okay, well, maybe I have a failing hard drive. Maybe I'm getting some data corruption. There's a whole conversation about doing checksums in the data in Petrov. Nobody even raised that point. I had this really interesting talk I attended many years ago by a gentleman named Jim Gray, who at the time was working for Microsoft Research in Silicon Valley. And Jim Gray is well known because he was one of the inventors of the two-phase commit protocol. He at the time worked for, I believe it was IBM actually, when he did that work in the 70s. And the idea was, this is how we can build transactional systems like the bank machine giving you cash kind of transactions. And he was talking about, God, my train of thought has derailed now, so what was I talking about? No, it was before that. Oh well, it'll come back to me. See, you guys aren't paying any attention either. Question in the back, yes. Can't hear you. I'm deaf. Hold on. I'll trundle up that way and probably actually remember what it was I was talking about by the time I get there, and then I'll forgotten by the time I get to you. So, I don't know. It'll come back to me. Tell these same stories. Nobody listens anyway, so it doesn't really matter. But thank you for trying. Because it was about failure, right? There's so many failure stories. It's oh, that's it, right? So maybe some of you have actually heard of this product called SQL Server. He was at Microsoft Research, right? So maybe you've heard of this product called SQL Server. And Microsoft has another product called NTFS, which is a file system that ships with Windows. I don't know, does anybody use Windows? It's almost as bad as Linux. Oh, crap. You use Windows? Yeah, me too. Yeah, of course, it's the best gaming platform there is right now. I mean, you can run your Steam Deck and you can put, games on that you're not supposed to be able to, and they kind of sort of work, but let's face it. I just want to sit down and play a game. I don't want to, with the hardware and the software. No, I just want to run my game. Great. So we got NTFS, we got SQL Server. Oh, yes, and they have this email server program called Exchange, which is still there, still around. And all three of them are databases underneath. NTFS is a key value store with a namespace on top. SQL Server is, in fact, a traditional DBMS. And Exchange uses an ancient database that is also used for Microsoft's Access product, believe it or not. They just super hyper customized it for their particular use case. So what he said was, the Exchange people added end-to-end checksumming on the blocks of data they wrote into the database. And they were getting checksum failures. They literally read data back and it didn't checksum. And so they went to the NTFS folks and they went to the SQL Server folks and said, do you guys see these problems? And they both said, no. And so then they had to start looking into it and investigating. And it turns out that NTFS and SQL Server weren't checksumming their data. So literally, you would read a block of data from the disk, and it would go, yeah, here it is, it's all fine, everything's hunky-dory, and it wasn't the data that you wrote. Oops. I hate when that happens. And those were real-world production systems. So the NTFS folks actually built a new file system called Refus, which includes checksums on the data, so they can detect those kinds of errors. They couldn't do it into NTFS because that would have required a disk format change. And NTFS hasn't changed disk formats since 2000. How many of you were born in 2000? Yeah, a couple, right? It was a long time ago. The guy who actually, he still is the development lead of NTFS and has been since at least 2000. is somebody I've known since 1996 because I taught him how Windows file systems worked in 1996. Oh my God. He wrote me a recommendation letter for the PhD program here. So, you know, I look him up, talk to him occasionally. Still does NTFS development. It still has a development team. They still work on it. They still make it work and fix bugs in it because people still use it because there's a few Windows users out there. We don't like to admit it because, of course, the Mac snobs will look down their nose at us and the Linux people will go, you should run Linux on your desktop. Okay. You know what? This is a good time for me to turn this back on and for you to repeat your question so that the listeners at home will be able to hear you and I will get closer to you so I can hear you too. He has a very soft voice and I'm very old and deaf.
Yep. So I was.
You can hold it.
Thank you.
It won't bite.
So before we were mostly saying that we need a backup so that in case the primary fails or there's like the cleaning lady turns off power
Right.
and such.
Whatever the reason of the failure.
But I mean, like the backup can be like a single unit, right? Because if the backup fails, then like do we have like how?
He's asking a question, I think, that I'm going to jump in here and say, well, but maybe a backup isn't good enough. Maybe because the primary and the backup are both in the same physical location. They fate share, don't they? They're in the same building. So if the power goes out to the building, I lose both of them. So how am I going to protect against that? That is a really good question, if that's the question you ask, and I'm sure it is, because... But in general, right. I mean, so, a cyclone comes through and levels the data center. And I wish I could make that up, but it really happens. Yeah. How are you going to protect against that? How does Amazon protect against the failure of an entire data center? They have multiple data centers in different locations. So it's just the same primary backup problem on steroids, isn't it? So now I have primaries and backups in a single data center, and then I have primaries and backups in other data centers. And then I'm replicating things both within the data center and what we call geo-replication, where I replicate them across those data centers. And one of the interesting things that came up last term, and I think it was really cool, there was a startup company, because I was joking about this, and then it crossed to my news feed, because of course, no doubt someone's listening. There was a startup company that got $5 million to fund the design of a lunar data center. Sorry? Why? Yeah, I know. Well, because apparently somebody thought $5 million was burning a hole in their pocket and they should give it to a startup company to go design a lunar data center. I was like, cool! That'd be a great project to work on. What a fun project. And then, why stop at the moon? Let's do Mars too. Well, now this becomes interesting because the time to get from the Earth to the moon is about a second. So it's roughly a second, give or take, 50%, to get a packet from the Earth to the moon. Does anybody know what the time to send a message is from the moon to Mars? Which is roughly the same as the amount of time it takes from Earth to Mars, by the way. Take a guess. Actually doesn't quite extend to 3 days, but it's pretty close. It's anywhere from 22 minutes to 2 days and 4 hours. It's crazy, and that's because, of course, Mars and Earth are at different distances at different times because they have different orbits. And in fact, you might not even be able to easily communicate with Mars because it's on the other side of the sun. Now that's a fun project to design because suddenly it was a discussion about clocks and time, and suddenly it becomes really interesting to reason about because you realize that the time that you send a message has nothing to do with the time that you receive a message. And this, I like this analogy because it makes it a lot easier to reason about, but it's the same exact scale when we're doing it in network scale on the globe. The time it takes for me to send a packet from here to there, like between two different racks, is relatively small compared to the time it takes me to send that same packet to a data center in I don't know, pick someplace exotic, Quebec City. You laughed. Wow. They speak French there, don't you know? How many people speak French? Very little, but an embarrassingly small amount. What? I'm sorry, how were they planning on sending a packet to the moon? Well, I'm not sure because I didn't actually see what they designed, but I'm pretty much sure they weren't going to use IP over Avian Carrier, which is one of my absolute favorite RFCs. And if you think I'm kidding, go look it up. There is actually an IP protocol specification for sending messages on carrier pigeons. And there are several follow-on RFCs for that. Somebody actually built it. That's the craziest thing. People do weird things. I have no idea. My guess is they would probably just simply use some sort of RF transmitter. The same way we communicate with anything that's sitting on the moon. But that's a cool question. Well, thanks. I really appreciate it. This was great. It sounds like you guys did read and get something out of this, or maybe not. Maybe just like, oh, this is going to be the easy class. I'm just going to show up and, like, click the boxes and get my 55 and be done. Cool. Whatever. I'll see you guys on Thursday, 5 o'clock. There's more reading to do because now it's chapters 5 and 7. I skipped 6 because it's lots more detail about bee trees, and I'm like, you're probably sick of bee trees at this point. Next week, we get into the interesting stuff. We get into transactions. And that's a wrap. So I'm going to turn off the stream. Thanks for coming. Glad I was able to get the sound to work. Well, hopefully I was able to get the sound to work.